In this video, we are going to find positive integers x and y such that x factorial plus y factorial equals x to the power y. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. I'm going to use a very special tool to solve this equation, and it's called the Bertrand's postulate. It says for any integer n that is greater than or equal to 2, there is always a prime number p such that p lies between n and 2n. For example, when n equals 2, then we can always find the prime that is between 2 and 4, and that's actually 3. So going back to this equation, my first idea is to pick the largest prime p that is less than or equal to the minimum value of x and y. And I'm going to make the following claim. Under the assumption that x and y are both at least 2, then the claim is that the minimum value of x and y is less than 2p. To prove this, I'm going to assume the opposite. That the minimum value is already larger than or equal to 2p. Then I'm going to use the Bertrand's postulate on the number p, so then we can find a prime number, say I call it q, such that q lies between p and 2p. We can do this because by definition a prime number is at least 2, so this prime number can be used for the Bertrand's postulate. But the fact that q is larger than p, okay, I would say this 2p is also less than or equal to the minimum value of x and y. So that means this prime q is somewhere between p and the minimum value of x and y. But the p is the maximum prime among all of those that is less than or equal to the minimum value of x and y. So this q contradicts the maximality of p within the range of min of x and y. So there's a contradiction, and that means, and the proof is done. So we know the minimum value of x and y is less than 2p. We continue solving this equation under the assumption that x and y are both greater than or equal to 2. So now we have a prime p that is less than or equal to the minimum value of x and y. So that means I can say that p has to divide x factorial, because x factorial is the product of the first x positive integers and p is one of them, and that also applies to y. So that means this p divides their sum, and hence x to the power y. Now since p is a prime, that means p has to divide each of the x. So p is not just less than or equal to x, not just dividing x factorial, it's also a factor of x. And maybe we can interpret that as x is a multiple of p instead. The reason that I say so is that we proved just now that the minimum value of x and y is less than 2p. And now we have the fact that x is a multiple of p. So let's see what happens if x is greater than or equal to 2p. Now from this we can already say that the so-called minimum value of x and y is actually just y, or else there will be a very clear contradiction. But now when we know that x is at least 2p, I know that p and 2p are members of the first x positive integers, so the product should divide x factorial. And more precisely, what I want is p squared is also a factor, and at the same time, we know that p to the power of y divides x to the power of y as well. And as we have y is at least 2, that means we also have p squared to be a factor of not just x factorial, but also x to the power of y. Then from this, we know that p squared must also divide the difference, x to the power of y minus x factorial, and from our equation, we know that it's actually y factorial. And from this, the only choice for y is that it must be also greater than or equal to 2p, or else we cannot find enough factors among the first y positive integers such that p squared divides it. But now these two inequalities brings a very clear contradiction, which contradicts that the minimum value of x and y is less than 2p. So that means the assumption is wrong. The assumption over here is wrong. And so that means as a multiple of p, it can't be even larger than or equal to 2p. So the only choice for x is that x equals to p. It is a very important result for our problem. Now as x is this prime number, we can go back to the original equation and consider the parity of both sides. Since x and y are both at least 2, that means x factorial and y factorial are even, and so is their sum. So that means x to the power of y is also even. But that means x is even. So that leaves us no choice, but x is not just a prime, but x has to be exactly equal to 2. Then we're almost done. So 2 factorial plus y factorial equals 2 to the power of y, and that means y factorial equals 2 to the power of y minus 2. And in fact, we can try them one by one, and we know that where y is at least 4, y factorial grows way quicker than 2 to the power of y minus 2, because the expression at the left increases by a factor of y, but for the right, it's just almost doubling the previous term. So I can just say this, y factorial is larger than 2 to the power of y minus 2. I might just omit the proof by induction. Therefore, I can try the remaining cases, which are just y equals 3, 2, or 1. For y equals 3 is a tick. For y equals 2, 2 factorial equals 2 squared minus 2, again is a tick. Or for y equals 1, 1 factorial is not equal to 2 to the power 1 minus 2. So that means the only solutions are 2, 2, and 2, 3. And this is our final answer. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.